Hello everyone. So in today's video, I'm going to solve two problems, one from limit or definite integration and second is from complex number. So first of all, this question we have, if value of s limit n tends to infinity 1 by 4 to the power n, pi is the product and I goes from 1 to 2n, n square plus I square the whole power 1 by n, and the value of this quantity is given as lambda times e to the power mu tan inverse mu to the power minus 4. So we have to identify the values of mu and lambda and then add them up. So I think I'm very bad at adding and all those easy calculations, because after solving I think that the student can do it and I loosely solve. So sometimes I do mistakes also. In previous one of the video I added some 31 or something as a 53, but it was 55. But anyway, that doesn't matter and that is not affecting the quality of the solutions I'm trying to provide. So let's try to solve this. And you wonder that I want to show something, that this is the thing where I work. I notice actually like this is the tab I have, and on tab you can see I simply jotted down all the questions and then try to solve it whenever I get, and then I pick some questions. And also some students are asking, this is by the way the GTE paper I got, and on this I have selected two questions which I found it will be worth sharing to you. So maybe I will refer it here. I'm just keeping it here so that my presentation is a little bit faster. Otherwise it will be difficult to think and explain at the same time sometimes. Okay, so this is the first question we have, and this is not a kind of a very new question, because you can understand and that this kind of questions you might have done many times. You can understand, you know that actually. So this is n to the power 4, not 4 to the power n. One temptation a student may have, that this is 1 by n to the power 4, it is out of the product part. So why not I can take the log only for this part. But in this case what will happen, that this will go on the power of e with the log, but this will remain down, and from there we are not approaching towards any 4 result. So if we make this term participate into the log, it may help better. So what we do there, for that I'm writing this as again as limit n approaches infinity e to the power log of 1 by n to the power 4 pi I goes from 1 to 2n n squared I squared 1 by n, and this is log. Now this log will separate this entire thing into two parts, so let me do it in a different way that time. But before that we can do this thing. Notice that this e to the power log is given here and n is approaching towards infinity. So the limit is actually applied to this term only. E is just sitting there like a viewer. So we'll keep it viewing everything, and I'm assuming this p as the limit n approaches infinity log 1 by n to the power 4 pi I goes from 1 to 2n n squared I squared to the power 1 by n. Now what will happen there, now that we have, first let me just take this question down. So after this what we can write it is limit n approaches infinity, and you notice that this term I'm taking as first term and this whole thing is the second term and applying log over it. So they'll give you log 1 by n to the power 4. So let me write it first, log 1 by n to the power 4 and plus limit n approaches infinity, and this is going to be log of the product by 1 to 2n n squared plus I squared to the power 1 by n. Now this guy I can write as 4 is out, so with this limit n approaches infinity minus 4 log n, and here I have this pi goes from 1 to 2n n squared plus I squared to the power 1 by n. If there it is given here the summation, sorry, the product, I can turn into summation by applying the log. So if you apply log here, so let us make it clear. Suppose I'm writing the first term, I will get n squared plus 1 plus n squared plus 2 second term and so on. So we can write this thing as limit n approaches infinity, the log of, not log of, summation of, and this is I goes from 1 to 2n and then log of n squared plus I squared to the power 1 by n. But notice what we can do better is 1 by n I can take out. This is, I'm writing as it is, minus 4 log n, and here limit n approaches infinity, summation I goes from 1 to 2n, and from there what I'm doing, that 1 by n I can take it out, it will jump off, so that will give you what, 1 by n log of n squared plus I squared. Now the problem with that, this 1 by n is actually going to help us for the definite integration construction of this limit. So we'll keep it aside, and this I'm just taking like as it is. So what we get it here is limit n approaches infinity, 1 by n I'm taking aside, I goes from 1 to 2n, and from there I'm taking the log, the n square common. And why I'm taking n square common? Because I need the r by n structure to make it to the indefinite integration. So for that it will become 1 by, not 1 by n, log of n squared plus the log of 1 plus I by n the whole square. And this is the thing here. This is the same thing, no problem. And now this I can separate in this way. Limit n approaches infinity, 1 by n, summation I goes from 1 to 2n, and this is going to be ln square. So this will become 2 ln n. And again this limit, summation I goes from 1 to 2n, log of 1 plus I by n the whole square. And since this 1 by n, I am also taking to this term, therefore that will become 1 by n there. Now you can just see this thing. This was minus 4 ln n when limit n approaches infinity. It's very difficult to, not difficult means it's actually impossible to evaluate this limit. You know that when n approaches infinity, log n shoots to infinity. So it's not a finite value, but it doesn't mean that our whole expression is approaching towards infinity. There's something going to help this thing, and this is here. It's a limit n tends to infinity, and here 1 by n. This, you can notice that this n is independent of the index I. Therefore, it's running from 1 to 2n. It means it is a constant. You're adding 2n times. So therefore, what we'll get it here is 2 times log, not 2 times, 2n times log n. So you can now realize that this thing will get cancelled. Why? Because this 2 times 2, 4, and this n will already get cancelled. So minus 4 log n, and this is 4 log n. So this 2 will get cancelled now, and I'm left with 1 by n summation I goes from 1 to 2n log of 1 plus I by n the whole square. Now it's not hard to understand that this is a directly a definite integration whose lower bound a is equal to, how do you find a lower bound? The I by n when n approaches infinity. So that is going to be 0, and what is the upper bound? Is a 2, and this 1 by n turn into dx, and this is going to be log 1 plus x square. Now when we simplify this whole thing and all, we can get the answer in terms of e, and after that we can compare the lambda and mu and to get the value of lambda plus mu. So I can leave this question up to here. After that, it's a simple integration by parts. I can assume log 1 plus x square as first function and 1 as the second function, and we can integrate it. Let's go to the next question. This question is a little bit interesting because it's from complex number. The question is that the omega not equal to 1 be at a 13th root of unity, and we have to find the remainder when this product again k goes from 0 to 12, 2 minus 2 omega to the power k plus omega to the power 2k is divided by 1000. So basically we have to find out the product, this thing, pi k running from 0 to 12 is 2 minus 2 omega to the power k omega to the power 2k. Now notice this is actually a quadratic in terms of omega to the power k. So why not we can think in this way, that if I assume a function fz which is z squared minus 2z plus 2, then I can say that we are interested to find out the product k goes from 0 to 12 of fz, where z is equal to omega to the power k. So there no need to take this fz, but I just took it. And before that, let's before just going to the solution, you can pause the video and try to attempt from here. It is actually for every question I should say, but still I got to say, that's why. Now see here. So you know this one fact, that suppose I have the roots x to the power n minus 1 is any polynomial, and the roots are, let's say, 1, then x1, not x1, let's say r1, root 1, then root 2, and dot 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 till root 3, not 3, root n minus 1. So if x to the power n minus 1 has n roots, means n roots of unity, and you know the roots, we can write them as this factor. So in this context, don't you think I can write in this way, that this is k is running from 0 to 12, and I'm saying that suppose I have those roots known to us, we can use something. So this I can write x minus 1, and since omega is the root of 13 root of unity, I can write, let's say, the first one as omega, x minus omega, then the second one is x minus omega squared, and no wonder x minus omega to the power 12. So these are the roots, so we just save it because we have to use it. And why I'm doing so, let's try to understand. So all that we have to find out the product P, which is nothing but K goes from 0 to 12 Fz. But Fz is this one. Fz is equal to z squared minus 2z plus 2. Can we also see that the z square minus 2z plus 2, if you know the factors, we can write them as a z minus alpha, z minus beta, where I am actually pretending, or maybe I'm assuming, that the f of alpha is equal to 0 and f of beta is equal to 0. Means I'm actually finding the roots of this, although we cannot find the real roots. So what are the alpha beta we can get? Alpha beta, I can directly write that a 2 plus or minus square root of b square minus 4ac, that is minus 4, and divided by 2. So that will give you 1 plus or minus iota. And these are the values of alpha and beta. One, I can take alpha as a 1 plus iota, or you can also say that beta is equal to alpha bar, which is 1 minus iota. Now, why it is useful to why it is useful expression? So this thing I have to evaluate z minus alpha, if you notice, z minus beta, where the z is not any z, is a z is equal to omega to the power k. So if you substitute this value there, it is going to be what? K goes from 0 to 12 omega to the power k minus alpha and omega to the power k minus beta. Now notice one thing. This is k goes from 0 to 12. When you are actually multiplying two brackets together up to 12, I can give this product term to both of them. It's not like you can give half and half. It should be up to 12 only. Please keep in mind. And this is the product we got. Now you can analyze this thing, that this product, it somehow we can connect with this. How we can connect? Notice that this is x minus 1, x minus w square. That's omega square, not w. I said w somewhere, so please understand it's omega. Now this is omega to the power k here, but notice that in this entire series, what was changing and what was fixed? You notice that the x was fixed and the omega value was changing, because this is also omega to the power 0. In the same way here also you notice that the alpha value is fixed because this is alpha is I plus 1. But only omega is changing. But to write this thing exactly x to the power 13 minus 1, I need to have alpha at the first position. Means what is not changing is always prior in each bracket. So this is alpha minus omega to the power k should be there. So what I'm going to do? Of course, I will take the minus sign, but there are 13 brackets. There are 13 brackets we have. And from each 13 brackets, I'm taking 1 minus 1 common. So that will give you minus 1 to the power 13. And this now product can be written as k goes from 0 to 12 alpha minus omega to the power k. Similarly, from the second product also we can write minus 1 to the power 13. And from here I can write k goes from 0 to 12 beta minus omega to the power k. So in this way we got this product, and notice this thing, that minus 1 to the power 13 and minus 1 to the power 13 together will give you the minus 1 into minus 1, that is positive 1. So they no need to write it again, and what we have is now here alpha minus omega to the power k and beta minus omega to the power k. So notice that all the products what I have, if I have x minus omega to the power k running from 0 to 12, I can write x to the power 13 minus 1. But at the place of x, this is alpha. So I can write this thing as alpha to the power 13 minus 1. And this is beta to the power 13 minus 1. And after that, it's not a difficult task, because you know that the beta is nothing but alpha conjugate. So I can write it as alpha 13 minus 1 and alpha conjugate 13 minus 1. This I can write alpha conjugate 13, and here I can write minus alpha 13 plus alpha bar 13 and plus 1. This alpha bar will become mod alpha, and this is power is 13, so it will become mod alpha to the power 26. Here this is nothing but you are adding one complex number with its conjugate to get the twice of real part of the same complex number, and that is 1. Now we have to analyze this value, or we have to evaluate actually. So how do we evaluate? So alpha, you know, that's a 1 plus iota, and it's better to convert into the Euler form. So root 2 e to the power I pi by 4 I can write, and here I can write root 2. By the way, magnitude of alpha is 1, root 2. So root 2 to the power 26. Here twice of, and what is the real part of it? So real part of alpha to the power 13. So let's see here, alpha to the power 13 is going to be root 2 to the power 13, and real part, this is going to be e to the power I 13 pi by 4, and real part of this is going to be twice of, not twice of, this is twice, 2 is already there, so this is root 2 to the power 13 and into cosine of 13 pi by 4, and that was 1. Now this is going to be 2 to the power 13 minus, this is 2 to the power 13 by 2 plus 1. So 13 by 2 plus 1 is 15 by 2 minus 15 by 2, and here cos 13 pi by 4. So 3 pi plus pi by 4, it will go into the third quadrant, so it will become negative. So it will make it this positive, and this will give you cos of pi by 4, that is 1 by root 2. After that, what we can do is this one, 2 to the power 13, and here I have 2 to the power 7 plus 1. Now we calculate it a little bit wisely. That is going to be 2 to the power 7 common, 2 to the power 6 plus 1 plus 1. So that is going to be 2 to the power 7 128, and here 65 and plus 1. So if you calculate it, I'm not sure what I'm getting, and whatever you get, that number you have to see if it is completely divisible or what remainder it is giving after dividing by 1000. So that's all for today's video. See you in the next video with some other GTA problem or any different problem. Stay math active.